we have seen that when the temperature is kept fixed for a box of gas, and you are allowed to change the pressure and the volume, we have seen how the pressure times the volume must be a constant. When the pressure is big, the volume must be small, so that when you multiply the two, you always get the same number for a given gas. Of course, if you do it for another gas or another volume or temperature, you will get a different constant for that other box of gas. Okay, now what I'm going to look at now is I'm going to look at how the volume changes with temperature if I keep the pressure fixed. So this time, I'm going to imagine that the pressure is fixed. How might I fix pressure? Well, you can imagine in a very simple setup, if I just put a block of wood there, to apply some pressure, and I just leave it there. Right? I don't change the block of wood, so the pressure is not going to change. It's just going to be a fixed pressure. So I don't actually apply any more force to this piston. So then what I want to do is, with this volume of gas, what I'm going to do is I want to warm it up. I want to warm it up. Okay. How can I warm it up? There are many ways. I probably wouldn't put a fire to it. It's a bit dangerous. So if I want to warm it up, I can maybe put some warm water around it, or put this in a warm bath of water, for example, or pour more hot water around it to change the temperature, or I can put some ice around it to lower the temperature. So it can be done fairly easily if we want, maybe a bit messy. Okay, so we can change the temperature, and as we change the temperature, we'll find that if you increase the temperature, if you make it warmer, pour some hot water around it, you'll find that this piston, this side of the box, would move up because volume increases. Right? We might have some idea that hot air expands and cold air contracts. So if you put ice around it, you'll find that this wall would come down, meaning that the volume would decrease. So again, this experiment has been carefully measured a few hundred years ago, and the values for each measurement has been written down. The values for the volume and temperature has been written down, and when this data, these measured values, okay, are plotted against each other. Say when volume is plotted against temperature. Let me just put in some numbers before it gets too abstract. So let's say this is degrees Celsius. Okay, so maybe that's 0 degrees. When I put lots of ice around it, that's 0 degrees, and that's 100 degrees. All right, 100 degrees Celsius, and I can achieve that if I pour lots of boiling water around it. Okay, I can go up to quite close, or maybe at 100 degrees Celsius. So this, and anywhere in between, right? Just add some cold water and the temperature can come down. So at each temperature, the volume can be measured. It has been measured, and we can plot a point of that on the graph. So this has been done carefully already a few hundred years ago, and the graph that is plotted, this is the kind of graph that was observed for a typical gas, like maybe even just air or of pure oxygen or nitrogen. So this was the kind of graph that was observed, a very simple straight line. That's it, really. It's a very nice straight line when the experiment was carefully done. Right, my hand is a bit wiggly, so it doesn't look quite straight, but it goes through a very nice straight line. So, okay, well, it's not surprising that when it gets warmer, at least not to us today, that when the gas gets warmer, the volume increases. But what is surprising is that it falls on such a nice straight line. Okay, now, and there is something even more surprising than that was discovered at that time. If you extend this line backwards, right? The mathematical term is called to extrapolate, right? Extrapolate. So if I extrapolate this line backwards, I'm going to do that now. Extrapolate this backwards. It's quite easy. Just put a ruler along here, get a pencil, and just draw a line along the ruler. Okay. Something curious was found. It was found at this point where the graph crosses, where the straight line crosses this temperature, this horizontal axis. This point was found to be at minus 273 degrees Celsius. Now today, all right, if you have learned something about temperature in science, you would probably have seen this number minus 273 degrees before, and you might even have heard that we call it absolute zero, and that no temperature can go below this temperature. But of course, at the time that it was discovered, some hundreds of years ago, this was not really understood. But the curious thing that was found was that, well, for one thing, when you extrapolate the line backwards, you get this number. So the significance wasn't, people didn't really know what's so special about this number. But they did find something which is quite strange, right? I mean, if you just draw any line backward, any slanting line backward on the graph, of course you'll cut the horizontal axis, and of course you'll get some number, right? If it's not minus 273, it would be minus some other number. So there's nothing actually surprising with that. But what was surprising was this. The scientists who did this measurement repeated the experiments for other gases. Other gases meaning maybe they change it to nitrogen, or they change it to a different volume. Okay. So they repeated for other gases, for different volumes, and they got other graphs, of course, other points, and they plotted them on the same graph. Okay. Maybe not literally, but they plotted them. And they plotted them, and they plotted, I'm guessing here, but I'm sure they must have done. It's so many years that have gone by. They must have done loads of experiments, plotted lots of points, and checked lots of data. Right? Otherwise, we won't be learning it today. Okay, right. So they just keep doing this and keep checking this, and they found that no matter what other gas you use, no matter well, I'm talking about the normal gas. I'm not talking about water vapor. I'm talking about the more typical gas like maybe oxygen, nitrogen, or even hydrogen, and maybe carbon dioxide. They found that when they draw the graph, when they draw this straight line through the graph of any gas or any normal gas and any volume that they use, they found that they all go through minus 273 degrees Celsius when you extrapolate the line backwards. That is a surprising bit. It's not just a random number, minus 273 now and minus 373 tomorrow and minus 473 for the next gas down the queue. For any gas, any normal gas, they find that, okay, maybe they're experimental error and it might be a plus or minus a little bit, but they all cross very close to minus 273. And because of this minus 273 number became to be important, to be considered important. Surely there must be some meaning to this number. Now, and there must have been a lot of speculations and theories and calculations and so on over the centuries. But eventually, for many reasons, one simple reason is that we might think that maybe when you make it cold enough, all right, all gases would fall to zero volume. Okay, but actually that doesn't happen. If it's cold enough, gases will just condense into a liquid and then the volume hardly change anymore. But in any case, after many years, it was finally accepted, okay, and lots of experimental checks, that this number is the absolute zero in temperature, absolute zero, and that no temperature can go below that value. So I'm sort of jumping ahead now, so I'll come back to this in a later session, but for now let me just finish off this session by actually I've digressed quite a bit by writing down what I started off trying to explain, which is actually just this straight line bit. Okay, so what I wanted to explain is that is that the graph of the relation between the volume and the temperature is a straight line. It is a straight line, but okay, maybe I've not digressed by so much, right? Because before I can write down the formula that is normally used to describe this straight line, I need to say that that we must make use of the Kelvin scale of the temperature. So instead of degrees Celsius, right, the usual way to write down the formula between V and T for a gas is to use the Kelvin scale. Now, and it is this Kelvin scale that developed from this new understanding that we have an absolute zero at minus 273 degrees Kelvin. So because of this, a new Kelvin scale was defined. The temperature in Kelvin is defined to be equal to the temperature in degrees Celsius, okay, plus 273. There is actually some decimal place after that, but I'll talk about that in another time. Right, I'll just mention it here and explain it another time. There's actually a 0.15 down here. Okay, so right, and just to avoid confusion, let me just change that letter to a theta. Change that letter to theta. So theta is the temperature in degrees Celsius in this example. So I'm going to reserve the big T here for the Kelvin scale. So if I want to use a Kelvin scale with where the zero is minus 273 degrees Celsius. This is the relation between the Celsius scale and the Kelvin scale. So in the Kelvin scale, we're using the Kelvin scale, therefore, the formula that relates the V and the temperature would be V volume over temperature is equal to a constant. Right? And the reason is that if you're using the temperature, the Kelvin temperature for T, I can imagine that instead of having the graph axis like this and like this, with the zero of the graph here at 0 degrees Celsius, I can imagine having a new set of axes where the let me try and redraw this, where the vertical axis goes through absolute 0. Okay, that's my V. And the horizontal axis, instead of degrees Celsius, the horizontal axis would be Kelvin, and that will be the new origin of my graph. So if I've this as the new axis, all of my graph, the volume temperature graph, would all go through 0. Okay, which is why the volume over temperature is a constant, right? Because all these points have the same along one particular graph has the same gradients. They have the same slope. And this law also has a name. This law is called Charle's law.